So hi, hello. Welcome to section number one of Chem 27. Woo! Ah! So I am like really like balls to the wall excited. Chem 27 is like one of my like top three favorite classes that I took in my undergrad. I've tutored it a few times, but this is my first time on teaching staff for it. I love the content for this class. It is unlike kind of any other biochem class in the country, and especially for those of you who are planning to go into medicine, it provides you with a really unique look into metabolism that most of your peers when you get to medical school will not have. A lot of times when you're in medical school, you are learning metabolic pathways, and the words kind of mean nothing. Like, you're just memorizing things. And I think a big goal of this course is for you to see some of the chemistry that is going on in these enzymes that underlie metabolic processes and understand how different cofactors work. And cofactors are often vitamins. So you walk away from the class with a really interesting perspective. That being said, it's very different. So like if you are looking for study resources for this class, it's going to be hard to find just because there isn't another course like this, which is frustrating. I'm sorry. So please do utilize like office hours and everything. I thought we'd start off with some introductions if we can do that since it's the first day. I know I had y'all fill out like the intro welcome form, but I'm wondering if we could just like go around and say some things. Is that too awkward? Is that okay? Okay. I'm going to turn off the screen sharing and then how should we do it? Should I call on people or is that like I feel like if y'all just like come out of the woodworks, it can be chaos, but also if I call on people, it's not great. I'm going to let it come out of the woodworks. So like unmute and actually I will keep sharing my screen so that we have the questions up so that you can be like, "Hi, who are you? Where are you from? Where are you at in your education? Why are you taking this?" Just to kind of share with the group, and then I'll do an introduction for me. So would anyone like to take it away? Please, go ahead.
Hi, my name is Jason. I'm 25. I am taking this course because I'm applying to vet school. But it's been a bit of a rocky road because I actually graduated like 2 years ago from Connecticut College with a bachelor's in classics.
Ooh,
Did a full pivot my senior year, and then I
yeah,
found at Tufts they offered what I learned was called a post-bac pre-med program
yeah.
that helped cover a lot of the courses. But then in the middle of applications, I came to realize for not every school has all the same requirements.
Work.
So I realized I needed organic chemistry too, especially for the school that I like, the target school that I was aiming at.
Yeah.
And my dad found the Harvard Extension program.
Hey.
So, he thought, if you're gonna get a grade from anywhere, here's probably the best place to look, which certainly is going to be a challenge because it's been probably a good year and a half since I touched organic chemistry one,
Yeah.
and I've definitely been trying to catch up. I've been starting to go through your section videos
Ding
for
dong. Yes. So hopefully
uh
the resources from last semester will be helpful. Feel free to watch me on two times speed. If you struggle with anything, feel free to send me an email and be like, "Hi, I'm reviewing this,"
I
and I'm like,
I will
"Who is
definitely
you?"
send you an email after this about because I've been going through the practice problems, like stuff that I
Yeah.
definitely know I need to work on,
Please,
but
or
I'll
stick
save
around
that for
for
like.
office hours, which will be happening like 15 minutes after section ends.
Oh, sweet, awesome, yeah.
Cool. Well, welcome. Who's up next?
I'll go next. Can you hear
Hi.
me?
Yes.
Okay. Hi, I'm Dina. I'm from California originally, but I've been here for a couple years now. I graduated with my bachelor's in 2023, my master's in 2024, and I'm going to vet school this fall. So Jason, I feel you with the whole taking classes, prerequisite stuff. This is my last prereq before I go to school, so I'm excited.
Oh, well, welcome. Hi. Also, I love the vet coalition. Are y'all hoping to
Yeah,
be big vets or small vets? Or like
I don't
large
know
animal,
yet.
small animal? Oh,
I don't
small.
know yet. Probably small,
Where?
but
I can go next. Can you guys hear me?
Yes, beautiful. Hi.
Okay, awesome. I figured I would also throw myself into the vet school coalition.
Whoa. Okay, pre-vets, watch
So
out.
funny.
The pre-vets are
Yeah.
taking over.
My name's Maggie. My pronouns are she, her, hers. Um, I'm from upstate New York, but right now I'm in Allston, Massachusetts, so right down the road from Harvard. I did a bachelor's in medical anthropology, so completely different from what I want to end up doing. And then I've been kind of like working in the veterinary field for the past 2 years, and I love it. So hoping to apply to vet school, joining Dina and Jason and that.
Very nice. Welcome. Any other pre-vets want to throw their hat in the ring and just like make a small legion? Or anyone else is welcome.
Hi, my name is Jordan. I'm from Texas, but I live in Philly now. I actually did the post-bac pre-med program at Harvard Extension.
Cool.
But then like lifed.
Mm-hmm.
So I'm taking this as like kind of an add-on. It's the last prerequisite I need to apply to medical school. So,
Very nice.
um, pre-med, anyone?
Hey, I'm sure that there are
Um,
people who can join the forces here.
yeah. Um, but yeah, what I did college at Swarthmore. I graduated in 2019, so
Oh,
I'm like very late, um, non-traditional student, I guess.
time is a construct.
Yeah,
Yeah.
it's all fake. Um,
Cool.
but yeah, hopefully this class isn't too much torture.
Hopefully not. I at least try to make it like pleasant torture if it has to be torture. Or pleasant torture is that doesn't make sense. I at least try to make it humorous torture. I don't know. But cool. I think that's our camera coalition. Does anyone in the non-camera coalition want to come forward and do an introduction?
Go.
Oh, one more. I'm
Um,
so sorry,
yeah.
Sean. I missed over
Uh,
you.
so my name is Sean. He, him, his. I'm from Bolton, Mass, so not too far. Um, I have a bachelor's degree in cognitive psychology, and I currently work in a molecular biology lab, so a little bit of a pivot. I'm a medical lab scientist,
Ooh,
so I develop genetic tests,
cool.
mostly for cancer, and I am mostly taking this class for fun,
Hmm. Well,
and we're
where are
paid
you
smart.
doing your research?
So it's not research. It's industry.
Oh,
We
okay,
do
industry. Yes.
assay assay development.
Very
It's
nice.
in native math, a
Hmm.
company called Pillar Biosciences.
Oh, cool. Well, welcome.
Thank you.
And that was our camera coalition. So sorry, Sean. Anyone else want to do introductions? You certainly don't have to, but please feel
I know
welcome.
you got a couple more people on camera too. They're on the next page waving.
Oh my gosh. There are so many people that there's a page too. Y'all. Y'all. Oh my gosh. Well, wait, why don't we do the group? Hi.
Yeah.
Hi. We can have the introduce yourself.
Okay,
Yeah.
well, my name is Vinique or Venick, depending on your accent. The cool kids call me V. Um, I was all we actually all three of us were also in Colton section last
I know,
semester.
which is why I was like, hi.
I know. And we're all taking it for in preparation for mid school, yeah.
Ding dong. And y'all are in the basement of the science center and the science library, correct?
Yes.
Yes.
Because I know those walls. I know that glass. Well, welcome. It's great to have y'all again.
Yay.
Anyone else?
I can go. Sorry, I don't have my camera on.
You're
Not
so
looking
good.
too great right now. I'm Rachel. Pronouns are she, her. And I'm from kind of also upstate New York, Warwick, New York. and I went to school at Colgate, graduated in 23, failed Orgo 2. So
here we are, yes.
retaking it because
Also, there's no shame in failing Orgo. Orgo is like crazy hard and also is very different at different universities. So you are certainly welcome here, and like we're all rooting for you.
oh, thank you. Yeah, hoping not to fail this time.
Ding dong.
And yeah, so I've been out of school a few years. I was a medical assistant. Now I'm a research coordinator at Dana-Farber.
Ooh, okay. Okay, Cancer. Cancer Coalition is growing.
You don't hear that a lot.
Work. Welcome.
Okay, thanks.
Any other? Oh, hi.
Hello, I'm Scary. That is my real government name. My pronouns are they, them.
Big
I am in the Bronx, and I have 2 useless art degrees, both are bachelor's, and I'm taking this class for pharmacy school.
Ooh, okay. Okay, pharmacy. I feel like I have not had many pharmacy students, but like my backup plan, if I ever get tired of teaching, is to become a pharmacist because there's so much biochemistry and I'm already like, we're in it. But work,
So the
welcome.
salary is just like desirable.
No, yeah, totally, totally.
So much shorter than med school.
Work, well, welcome.
Thank you.
Okay. Any other intros? Last call for intros. Going once. Going twice. Gone. No more introductions the rest of the term. We all just know each other now. So I, since I have the power to present things, have made a slide. So things about me. My name is Colton. I take any pronouns. I'm non-binary. I'm a Virgo. I'm out here in Georgia. I'm a Southern Belle, a Georgia peach. I did my undergrad at Harvard, and I was in the class of 2020, but life things. I graduated in 2021, and also like COVID things. It was kind of funny because we didn't have graduation because it was in the middle of COVID, so they like just emailed us our degree. So now I have a JPEG on my computer that's my Harvard degree, I guess. .jpeg. At Harvard, I was in Courier House. I transferred from Elliott. My big like extracurricular thing that I did was musical theater. So these are from different shows I music directed. One was a musical called Dogfight. One was Chicago. And then the other one was a musical adaptation of Shakespeare's The Tempest. What do I do? Well, I have a dog. I take care of her. She might come around. But main things, I work as a tutor, a math and science tutor, mostly for high school and college students, mostly like SAT, ACT stuff, and then like pre-med curriculum broadly, because that's what has demand. And I'm also a caretaker for my dad, who is a little bit older, has some health things. As part of that, I am running the family business, which is radio stations. So I am also a radio mogul, reluctantly, at the tender age of 28, but I'm trying to not be a radio mogul. So if you know anyone who wants to buy radio stations in South Georgia, let a girl know. This is my first year TAing for 27, which I said at the very beginning, but I'm very, very excited. I have the enthusiasm as if it has been I have the enthusiasm as if it's my first time teaching it. But I've been TAing or TFing with Harvard broadly for about 7 years now. My main course that I do is the summer Chem 1 class, Chem S17. And so that has been a staple since 2019 for me. I also like periodically take classes and I'm like low-key post-backing, like not in a like structured program, but I've taken some extra undergrad courses in mathematics and biochemistry and music, and I do like choir. Eventually eyeing some different PhDs for options, but not sure exactly where it's going to go. Oh yeah, I guess my degree was in chemistry and music, so I've always been a little Hannah Montana, best of both worlds with like STEM and humanities. But yeah, that's kind of my deal. But I really like teaching, and I know that it takes up time to do introductions in a first session, but I hope to get to know you over the course of the semester and office hours and everything, so thank y'all for indulging me. Cool. Well, let me walk you through the game plan for today. So we have kind of 4 big topic areas that we're going to discuss. For those of you who had me last semester, she's not going to be looking as pretty for section notes. So a lot of my section notes now are like handwritten. This document was posted on Canvas at 5:50 p.m. because that was when it was ready. These are my like first time preparing the lessons, and so this is kind of very much in draft form. Just for context, I normally do things like this, where it's all like typeset and fierce and color coded and blah. But for now, we are making do. We are first going to do a little tour of the amino acids, and then I swapped these at the last minute. We are going to do like 5 minutes talking about amide bonds just to kind of set you up for that PSET question. We're going to spend a lot of time on pH and pKa and how that involves amino acids and peptide chains and do some practice questions involving that. And then I'm going to end with like a 10-minute kind of spiel on protein folding of like how do we explain protein folding, what is the hydrophobic effect, how do we put all this together. So that's the general game plan. So, without further ado, welcome to the amino acids. I know that y'all are not required to memorize this. I very much think you should. If I was like the god of this class and could like make all the decisions, I would make this like you have to memorize it, and I would make there be a quiz on week 2 for like a week, memorize them. Because like amino acids are the language that we use in biochemistry, which this class really is a biochemistry class as well as an organic chemistry class. So if you were having to think or refer to like a sheet of the amino acids, it would be like translating a foreign language and you're having to look up the words in the dictionary each time. Or like another metaphor is it would be like reading by sounding out words rather than just reading. And so I would say by like next Monday, try to get these memorized in terms of the name, 3-letter code, 1-letter code, and be able to draw them. That I know is a big ask, but it is going to get you in the mode of this class. And going forward, you are going to be drawing amino acids every week, on every homework, on every exam. And so it will pay back dividends to invest the time now. It's kind of like when you start in organic chemistry and they're like, memorize the functional groups. And you're like, sure. And then you don't know the functional groups. And then it's like, is that a ketone or an ester? So because I'm asking you to memorize it, I'm also going to go through some of my little mnemonics with these, which hopefully doesn't make you immediately lose respect for me because some of them are really, really smooth-brained. Yeah, without further ado, so we are kind of breaking them into little families of polar, nonpolar, and charged. And I think I'll start up here with the charged. Oh gosh, okay. So, first off, we're starting off with aspartic acid, which also goes by aspartate. So, the reason it has 2 is because this is a carboxylic acid. But if you deprotonate it, like it is at physiological pH most of the time, it's a carboxyl 8. Ooh, ding dong. So you might see both of them used. And that's kind of the thing why we have 2 names for them. The 3-letter codes for each of these are pretty easy. Like, it's just the beginning of them. But the 1-letter codes are a little weird. So for glue, my favorite thing is like, it's literally like the word glue. Like you just have the silent E at the end of the word glue. Glue. So for this one, it's a little bit, this is juvenile. And so forgive the juvenile joke of it all. But I imagine a kid at the back of the class being like, Aspartic acid, more like aspartic acid, and that's the D. It's really dumb, but that's how I memorized it, and that's what I think every time I look at these. So there's that. The other thing that you should know about this is when we have something that begins with an ASP, there is always one carbon before our carbonyl. But when we have something that starts with glue, there are two carbons before our carbonyl. And so our like little guiding force is asp is 1, glue is 2. Fair enough. And I know I said I was like, let's do charge, let's do whatever. But part of how I laid out this document was to really make it just easier to memorize things. And so I might just go straight down and be like, oh, well, these are asp and glue as well. And does our rule work? Asp is 1 carbon and then a carbonyl. Oh, glue is 2 carbons and then a carbonyl. Oh, great. So both of these are polar. And the functional group here properly is an amide. Carbonyl with a nitrogen with some hydrogens. And the big thing here is these hydrogens are not acidic. You are not removing those hydrogens at all. But these are really important amino acids broadly in metabolism for shuttling around nitrogen. And when we get to our last unit, we'll do a lot of reactions that are involving these. Now, let's look at them. Because nitrogen is so important for both of these, their names, they just insert an N. So instead of glue, it's GLN. Instead of asp, it's ASN. Fair enough. And to remember, glutamine is Q. Glutamine, more like cutamine. Oh, cute, cutamine. That's the Q. And then asparagine, I just imagine the VeggieTales little asparagus. So I'm like, that's a nice asparagus. And then also like N is important. But so we can see some trends here that will help us. And again, if you have the asp is 1, glue is 2, you kind of have 4 of these down in terms of the structure. From there, let's look at histidine. So histidine's the bane of many Chem 27ers' existence in terms of drawing, because it looks like a lot to draw. So it is 1 carbon and then this weird ring that's called an imidazole. And I think that just like you're memorizing structures, this is a structure to memorize. And we're going to have like 3 or 4 total structures that are part of amino acids that I think is good to know to orient you. So the biggest thing I think I can do here to help you is, because like this, his, H, obvious. The biggest thing would be help drawing. So what's the process of drawing histidine? So we do our little, like whatever it's coming off of, we do our 1 carbon, and then we start at the end of our like 5-membered ring. And when you're at this branch point, starting the 5-membered ring, you put on a double bond on one side and a bond to a nitrogen on the other. So that's kind of step 1. Step 2 is once you have this, you complete the ring. And the important part is just that you have the nitrogens that are 1 carbon away from each other. So I had this, and now I'm going to flush it out with 1 more nitrogen and a carbon between them. The last thing is for your 2 ends that are here, for one of them, add a hydrogen, and the other one, make a double bond to a carbon that does not already have a double bond. It does not matter which left or right that you do. So like when I did it over here, I made the NH on this kind of right one, and when I did it over here, I made it on the left one. They are the same. We are like pancake flipping it over. They are the same molecule, so either way works. This imidazole ring is also aromatic, and so you are going to be able to I actually don't know where I was going with that. It's aromatic, FYI, I guess. And I didn't explicitly mention the pKa's here, but the pKa's of the D and E are about 4. And then the pKa of the histidine 6.4, so really close to the physiological pH of 7.4. Then we have arginine. Arginine's a fun one. So you do 1, 2, 3 carbons, and then you have this weird molecule called guanidine. So guanidine is like, what if you had an imine, a carbon-nitrogen double bond, and what if it was amides on both sides? What if, right? It is just a really great way of holding a bunch of nitrogens. It's really similar to like urea in structure. And so what I imagine is this is a treasure trove of nitrogens. And who's seeking treasures? Pirates. And what do pirates say? Arr. Arginine. That's how I memorize it. Again, hopefully that helps you, but I'm just going to keep plowing through. Now, lysine. Lysine has a pK of 10.5 down here, and my mnemonic for it is really dumb. It's 1, 2, 3, 4 carbons. Actually, I want to double check that. I think it's 4 carbons, but then I made a typo right below. Yeah, it's 4 carbons. So I just put the wrong thing down here. Apologies. So it's 1, 2, 3, 4 carbons, and then suddenly a nitrogen. And so what I imagine is conspiracy theorists being like, so there are 4 carbons, so we expect another carbon after that, right? No. But no, my dude, it's a nitrogen. It's a lie. Lysine. I hate everything. I'm so sorry. And then I imagine for K being the abbreviation of lysine, someone like listening to the conspiracy theorists and going like, K, it is what it is. We plow ahead. So let's now go on to the polar. So I'm going to start down here. So we have serine. Serine is 1 carbon, and then we have an OH, an alcohol. pK is 13. It's not really acidic enough that it's going to be charged often in proteins, but it can be in certain mechanisms that we'll see going forward. It's polar. My little way of remembering this is serine. I think about like searing your hand on the stove and then going like, oh, hot. OH, serine. This is just how my brain works. Cysteine. Cysteine is one of my favorite. It's literally like, what if serine had a sulfur instead? So it's a 1 carbon and then an SH. It's also polar. Its pKa, I didn't write here, is about 8. Oh no, I did write. Cool. And I have a story time about this one, which is that one of my best friends in the world, Katie, in high school, she had a cyst on her wrist. And I was like, that's so cool. I was from like playing cello. And then she was like, shh, don't tell people about my cyst. And now I tell every biochem student I ever teach. And so that's why cysteine is SH. Then down here, we have this kind of funky one. It's like, what if we had a serine and then we added a methyl on it? So another way of thinking about it is there are 1, 2, 3 things attached to, like, as our R group, I guess. A methyl, a carbon in the middle, and an OH. 3 things, threonine. It is also polar. Its pK is the same as serine, about 13. And one of the cool things is it introduced a second chiral center into the molecule. And this, we call the carbon right next to the carbonyl alpha carbon, and the one that's one more away, the beta carbon. So this beta carbon is actually R, whereas we had said in class that almost all of the amino acids at the alpha position are S stereochemistry, except for over here, cysteine is actually R. And so I put that in the kind of general notes. Typically, we are not going to ask that you worry about stereochemistry for this, but I just wanted to provide it here so that you can kind of see it. Now, while we're on the note of having a second chiral center, the other amino acid that has a second chiral center is isoleucine over here. So we have 1, 2, 3, 4 carbons over here. And this carbon, in the context of the side chain, is connected to 2 other carbons. So it is a secondary carbon. So this is sec-butyl, and butyl because we have 4 carbons. Another way of thinking about this is an isomer of leucine over here, which has 1, 2, 3, 4 carbons. These 4 carbons have like a fishtail at the end, and so this is technically isobutyl. because we have moved our methyl one away from the end rather than just having a straight chain. Both of these are classified as aliphatic, which essentially means alkanes. Like they're boring. Nothing's going on with them in terms of polarity, things like that. But isoleucine, I said, has a second chiral center at this beta carbon over here. And this second chiral center stereochemistry is also S, just like the alpha carbons for everything. Cool. So isoleucine, ILEI, that's pretty self-explanatory. We said that this is an isomer of leucine. Leucine here, the way I think about it is leucine is like a long V. So like we have valine, which is straight up just a V. And like that's an isopropyl group. So we have a V, valine, val, V. That's all pretty like good. But leucine, I think we still have a V, but we have an extra carbon. So it's a long V. I also think about Lucy from the Peanuts cartoon. And what was I going to say about it? I was like, and Lucy is 4, like a butyl, but she's not 4. She's like 8 or something. I'm trying to make it work. I don't think that it's that good of a mnemonic. So leucine, long V. Then over here in this corner, we've moved into the nonpolar land, by the way, which I'm sure you picked up. Again, this is kind of a jumbled mess going through all of this. But we have glycine. Boring. She's boring. Give us more. Our group's a hydrogen. Boring. So I don't really have a way of memorizing that glycine is just an H, but glycine, she's just the boring girl. She has no chiral center. But because it's so small, actually, she is like really, really like flexible. And so glycine often plays a really cool structural role in proteins as we think about folding and making our alpha helices beta sheets. So it is one of these 2 amino acids that are often associated with more structural roles. The other one that's highly structural is proline over here. And proline, our R group, fuses with the N-terminus to make this parole ring, this 5-membered ring. It is also structural, but it is structural in that you are turning. So like proline is often used when you're doing, like, let's say you're doing a beta sheet and you're going this way and you want to try to turn and go back this way. It is used to help do this turn because it has this ring structure that's going to kind of shift everything. My way of remembering this, which I don't have a picture for, is like proline. She's a professional. She is turning this ship around. She is getting things done. Proline, Miss Professional. I also think about like a professional jeweler or something because it's a ring. But I couldn't find a good image for it. Then moving on up, we talked through valine, which is pretty easy. For alanine, the R group's just a methyl, and I think of some weird dude named Alan who's just like always standing in the corner. Alanine, like Alan is here and it's just a methyl, just like not talking to anyone. Methionine, she's kind of cool. She's hard to synthesize as well, and she's involved in some cool pathways. She is 2 carbons, a sulfur, and then a methyl. So when we have a sulfur with carbons on either side, that's called a thioether. It's like an ether, an oxygen with carbons on both sides. And then it's a thioether followed by a methyl. And so how do they get the name methionine? Meth-thio. And then the most amino acids just end in ene. So methionine and then met and M are pretty easy from that. Then we have our aromatic nonpolars. So first we have phenylalanine. She is 1 carbon and then a benzene ring, which remember we call a phenyl, PHENYL ring. And another way to think about it is it's a phenyl group plus, remember we said CH3 as the R group, 1 carbon, that's alanine. So phenylalanine. Oh, okay. So the abbreviation PHE, pretty obvious. And then they just went in a phonics direction. So they were like, no one uses F, so let's make this F for phenylalanine because that's the sound. After that, over here, you have tryptophan. So tryptophan has one carbon and then this massive ring. It's the largest amino acid by far. And this is called an indole ring. It's aromatic. And in terms of drawing it, the way I normally think about it is you draw your one carbon and then start the ring, kind of like you do histidine. And then the two things that you have here are a double bond and a single bond. Once you've gotten that double bond and single bond on, I think about completing the 5-membered ring and putting a nitrogen at kind of the crown of that 5-membered ring, and then starting our benzene ring. And then after that, once you've started the benzene ring, you just complete it and add the double bonds. And then you have tryptophan. So tryptophan is big. Do you know what else is big? A car. Like a Subaru. How do little kids refer to Subarus? Subarus. That's why this is W. We're going on a trip in the Subaru. Again, I can't help myself but to think of it this way. Every time I see tryptophan, I think tryptophan. I was talking with a former student recently, and she's in med school and was taking like a shelf exam for like a psych rotation, I think. And there was a question about different neurotransmitters, which a lot of neurotransmitters are really close to amino acid structures. And she was like, okay, tryptophan, ketamine, like it just sticks with you the more ridiculous it is. And then I think the last one that I've yet to talk about is tyrosine. So tyrosine is like, what if we had phenylalanine and then we just add an OH on it? And remember, we have this term from organic chemistry that if we have a benzene ring and an OH on it, that together is called a phenol. And that's more acidic than a normal alcohol. So we have, this is tyrosine. TYR is pretty straightforward for that. And then the one letter code, we choose the Y just because it's a unique letter and we've run out of letters. Because we have 20 amino acids, we have 26 letters, we are scraping the bottom of the barrel for some of these. So, I know I have not taught you science here, but hopefully this was helpful in terms of like orienting you, pointing out some of the patterns between amino acids. I've tried to kind of put some of them structurally together of like these and like this group and then the like. Hopefully that makes this be like less of like this is random information to be memorized. And I got a question in the chat. These are already posted on Canvas. They're under the module for section, but I only posted it like 10 minutes before section. So, cool. Any questions about these so far? Or have I made any mistakes? Because again, I am like generating this for the first time, so it has not undergone rigorous proofreading. If you have a question, feel free to like unmute and just ask. In the chat, can you put your favorite amino acid? Mine's cysteine, just because my friend Katie, I think of her every time, and she's like my best friend. She's doing a MD PhD at Yale right now, so very proud of her. She overcame her cyst. Arginine, okay. Histidine, cool. Some people like a challenge. Histidine. Arginine, the pirate bounty. Arginine. And arginine and lysine are actually both pretty heavily involved with like chromatin condensation, like wrapping around histones. And whether or not you have the positive charge on those helps determine whether or not the DNA is expressed or it's not. Okay, histidine, ding dong. No other cysteine girlies out there? That might just be me. Then again, sulfur, I just think she's neat. She's gonna do a lot of cool chemistry with us this semester. Hey, I just met you. Okay, well, I see you. Cool. Okay, so now we are going to do like a 3-minute aside on amide bonds. So this is mostly a recap of OChem 1 things. Amide bonds are pretty darn rigid. So oftentimes when we think about a polypeptide that has a bunch of amide bonds on them, we think about having all these rigid planes, and then we have atoms in between that can rotate. So we could rotate around this bond really easily, like winding around town, doing Newman productions, but these are rigid. And so why? Well, it has to do with the fact that this nitrogen might appear sp3, but by our one exception to the rule, our rule being the number of electron domains determines the hybridization. Normally, if we have 4 electron domains and a hybrid, an electron domain just means lone pair or bond area. So normally if we have 4 electron domains, we're sp3. If we have 3 electron domains, we are sp2. And if we have 2, we are sp. So like, for example, this has 1, 2, 3 electron domains, so it's sp2, sorry. This one over here has 3 hydrogens that are implied. So for those who have not done OChem in a while, remember every end and bend is a carbon. So carbon, carbon, carbon. And then we imply hydrogens to make it neutral. So carbon wants 4 bonds, so there are 3 hydrogens on this one, 2 on this one, 2 on this one, so on. So here we have 3 bonds to hydrogens, 1 bond to another carbon, 4 electron domains, sp3. If we do that on this nitrogen, it appears to have 1, 2 bonds to hydrogen, 2, 3, and a lone pair, 4 electron domains. We would think it's sp3. But the one exception to this is called the neighbor rule. If it appears to be sp3, if it has a lone pair, and if it's adjacent to a pi bond or a carbocation, it will not be sp3, and it will in fact be sp2. And we can draw our curved arrows and show the resonance structure here. So we can show the actual resonance. And because of that, that is what is making this rigid, making it so that we don't rotate around it. We often talk with amide bonds about there being 2 stereoisomers that can be forced or formed by this amide bond. But it kind of feels weird to talk about them as stereoisomers because these look like single bonds, and we know that we can rotate around single bonds. So don't be thrown if you see this word stereoisomers. It's because we have this double bond character here between the carbon and nitrogen. So I have labeled these carbons on the other side alpha carbons. These are carbons that are 1 away from a carbonyl. So remember our alpha carbon nomenclature, and the alpha carbons are what the carbons that are going to have our side groups on them. So my biggest tip for drawing cis and trans amide bonds is make your C-N bond horizontal. So often we're doing the zigzaggy, and I think it makes it just harder to see when you are doing it. So if we make it horizontal, we see that there's one way that we can write it where our alpha carbons are 100% opposite each other. And if we draw the resonance structure, we see, on an alkene, these are trans. The alpha carbons are trans to each other. We could rotate around this 180 degrees, and then we see that our alpha carbons are on the same side. They're cis to each other. And here's the resonance interpretation here. So for this rotation, the delta G is relatively low. So the actual energy difference between this and this is not huge. But the delta G double dagger is very big. And remember, delta G double dagger, we're talking about the transition state. Or we're talking about activation energy. So while the cis and trans might not be super far apart in energy, let's say the trans is a little bit more stable down here and the cis is a little bit up here, small difference, it might take a huge amount of energy to actually rotate between it. And why is that? Why does it take a lot of energy to actually rotate here between it if the delta G between the cis and trans isn't that high? Well, remember, we are only having resonance because we very specifically have all of our p orbitals lined up exactly. As soon as we start to rotate out of plane with our other ones, we have lost resonance. We have lost a stabilization, and that is that high energy cost for our activation energy. So I already said the tip of draw the CN horizontal when you're doing it. Another tip is remembering both the carbonyl carbon and the nitrogen are sp2 hybridized. And so we know that the geometry of that's trigonal planar, so 120 degree bond angles between everything. And then lastly, part of the P-set, what I think is the hardest question on the P-set, is asking you to draw the cis and trans isomers in a proline as part of a longer chain. And just a piece of terminology that I think would be helpful as you are trying to explain that is if we call this the alpha carbon, the one right next to the carbonyl, if we continue counting, this is beta, this is gamma, this is delta. And so I just wanted to tell you that this is called the delta carbon. And I think that that might help with some of your explanation. Of course, you're going to be drawing structures, but that is my 5 to 7 minutes on amides. Any questions here before we go on to pH and pK? And I promise in pH and pKa, I will do less talking and we will work actually problems, and that will be helpful. I feel like we're having a moment of silence for something, but no, there's no occasion. Moving on, let's talk about pH and pKa. So if Gen Chem has been a while for you, remember P just means take the negative log of something. So pH is taking the negative log of your H plus concentration, and pKa is taking the negative log of the Ka, which is our acid dissociation constant. And so this was all within chemical equilibrium unit of Gen Chem, where let's say you have some acid, you have water, and then it's deprotonated, and then we get the conjugate base of our acid, and then H3O+, because this thing was our base. It took a hydrogen from the acid. Ka, our equilibrium constant for acids, is the concentration of the product molecules over the concentration of the reactant molecules. So we would do A minus concentration over times H3O plus conversation times H3O plus concentration over HA concentration. We leave out water because it is a liquid state of matter, and for equilibrium we only care about aqueous concentrations or gaseous concentrations. But both of them are going to be used a fair amount. Most OChem classes really are using pKa, whereas most Gen Chem classes are using pH. In biochem, we use both. And pH typically is describing the acidity of a solution. It's what is the acid environment of the solution at hand, whereas pKa is describing the acidity of a single hydrogen, so it's much more specific. And our golden rule here of using these together is if pH is lower than pKa, our species is protonated. So with this, there are two types of acids, and I, to be so honest, have never really used this and don't think it's that important. But I think having terminology can sometimes be helpful. But an HA-type acid is an acid that is neutral in its protonated state. So when you deprotonate it, you go from being neutral to being negatively charged. So a classic example of that would be a carboxylic acid. It's neutral when protonated, and when we deprotonate it, we have a negative charge. Cool. BH plus type is an acid that is positive when protonated. And so it's positive when protonated, and then if we deprotonate it, it goes from positive to neutral. So maybe an example of this would be OH2 plus going to OH. So we would say that this is a BH plus type acid. Again, just kind of nomenclature. So let's look at an example here. NH4 plus, which is a BH plus type acid, has a pK of 9. And so let's consider NH4 plus in a solution that's at pH 6. Well, pH is less than pKa, so we know it is going to be protonated, and its protonated state of NH4 plus. So it's mainly NH4 plus. But we're always going to have some NH3. Remember, this is like an equilibrium, which I should, in my tiny, tiny drawing, have it backwards. It's an equilibrium. And so because this can feel kind of foreign to y'all, I wanted to introduce this rule of thumb that was really, really helpful for me when conceptualizing pH and pKa things. So pH and pKa, because we're using logarithms, that is a scale that works in terms of orders of magnitude, or powers of 10. So if we have pH and pKa, we said that protonated state is favored because pH is less than pKa, and they have a difference of 3. So what our ratio is the ratio of NH4 plus to NH3, we know this one needs to be the bigger number because protonated is favored, is going to be 10 cubed to 1. And again, we're putting that 3 here because these are orders of magnitude, or powers. So for every 1,000 NH4 plus molecules you'll have 1 NH3 molecule. And in percentages, it's 99.9% to 0.1%, which, like, again, it's mostly going to be this, but you are going to have a little bit of this around. And as our numbers get closer, then the ratio changes. So if we went up to pH 8, our delta is only going to be 1. pH is still less than pKa, and so protonated state is favored. But now the ratio is only 10 to 1. So for every 10 NH4 plus molecules, you'll have 1 NH3 molecule. And so that now gives you a very different lay of the land of like what is the makeup of our solution in terms of the ratio of these. Going one step further, if it's 12, our delta is 3, but now pH is greater than pKa. And so it's 1 to 10 to the 3 in the other direction. So for every 1 NH4 plus, we have 1,000 NH3 molecules. So let's have y'all kind of try it here. So let's take serine. Serine has a pK of 13, and let's do it at roughly physiological pH at 7. So first of all, is serine an HA type or a BH plus type acid? Can you put in the chat what you think? And if it can potentially be either, which one do you think is associated with pK of 13? Why are y'all laughing in the chat? All I'm seeing is ha, 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 ha. Okay. Dad joke. Yes, y'all are totally right. It's HA type acid because our hydrogen that's acidic is already there. So we know that it is going to be going from OH to O minus. Why is it not OH2 plus, this BH plus type? Well, we know an oxygen with a positive charge, that is going to have a pKa similar to H3O plus, which is like -2. And so we would expect a very different pKa value if this is what we're talking about. So oftentimes you're going to have to use your existing knowledge of pKa's in order to kind of marry this information and like intuit, is this an HA type or a BH plus type acid? Cool. So which species is dominant and what's the ratio? Well, is pH less than pKa? Well, that's 13, that's 7. Yeah. So the protonated is dominant. Okay. So what is our like protonated to deprotonated ratio? Okay. Well, between pK and pH, that has a delta of 6, a change of 6 between those. And we have more of the protonated. So 10 to the 6 to 1. So there is a 1 in a million odds, basically, of having this deprotonated serine. Really, really uncommon to just in the wild encounter a deprotonated serine. And yet, in the next 2 lectures, we are going to show you a negatively charged serine. Why can we do that? What's going on? So they haven't really said this yet in lecture, but we can mess with pKa's a lot in biochemistry by controlling the environment around the amino acid. So if you are inside a protein, you are essentially tailoring a suite of amino acids that are right nearby, and it can change the pKa very dramatically. And we call this a microscopic pKa. I got a question just walking through how I got this ratio again. So remember, this is on the orders of magnitude scale, so it's 10 to some power. I got this 6 from, there are 6 units different between the pH and pKa. And I know that the side that's 10 to the 6 is going to be the protonated side, so this over here, because pH is less than pKa. So I know that the protonated species is dominant. Cool. And then another one really, really quick. If pH is 7.4, pKa is 6.4, who is dominant? What is it? And this is our histidine, by the way. So pH is greater than pKa. So the deprotonated is dominant. Wow. Drawing a histidine with people in the room is really stressful. So, in our deprotonated to protonated ratio, there is a 1 pKa and pH difference here. And so, if deprotonated is dominated, we have a 10 to the 1 to 1 ratio. So, for every 10 histidines that are neutral, there's 1 that's going to be charged, which again is really, really close. Fallon, what's up?
Hi. So for these, when we're thinking about protonation and deprotonation, are we only thinking about the side chain, or do we ever have to think about the ends as well?
So right now, or like broad strokes, you're mostly just thinking about side chains, because in normal proteins, you're going to have way more side chains than a single N terminus and a single C terminus. But we're going to do some examples that involve short peptides where you are going to use the N terminus and C terminus of a chain. And we'll see that in just a little bit. Cool. Okay, any questions on this before we jump into the first big kind of practice question? And the other thing is like the ratio here, the rule of thumb that I'm going over with you, you will never be tested on that. But I really do think having some sort of like sense of like, well, how much more do we have of one or the other makes this feel way more intuitive and reasonable rather than just some random thing that we're telling you. At least it did when I learned it. I remember like being taught this rule of thumb and like doing a hard blink at it, like, oh, okay. But other questions on pH and pKa so far? I keep just imagining tragic events to really meet all of the moments of silence that we are creating here today. But hey, that's the nature of Zoom teaching. So feel free to ask questions anytime. You can use the raise hand function or put in the chat. So let's start out with practice number 1. This thing has a pK of 7.1. Figure out what we mean by that. That's, again, this kind of idea of like, what type of acid is it? HA plus, or HA or BH plus? What's going to be the like conjugate of this? Like, if it's an acid, what's its conjugate base look like? At pH 7.4, which species is dominant? So let's try that out. Okay. So pKa, we know we're referring to a specific hydrogen. Which hydrogen are we probably referring to? Well, we have some CHs, but CHs are never really acidic, unless we're really talking about enolates, but the ones on benzene ring, never. So OH, okay. And do we think that we mean this OH, or do we think that we mean OH2 plus? So do we want the HA type or the BH plus type? Can you put in the chat what you think? If we have a pK of 7.1, do you think we're referring to the HA type or the BH plus type? I'm really missing the joke, guys. Why are you laughing? I hate everything. Yes, you're totally right. This is going to be HA. So we know alcohols normally have a pKa between 14 and 16. And for a phenol, which this is really close to a phenol, they have pKa's of around 10. So this is close enough that it's probably in that range. So let's draw our conjugate base here. So we are going to have the same ring, and we're going to have an O minus. And so this is our A minus form. And then at pH 7.4, who is dominant? Okay, well, pH, and we have pKa is 7.1. And maybe also I will like highlight this as our H. So pH, is it less than pKa? No. So pH is not less than our pKa. So deprotonated is dominant. So this is our dominant species down here. But these are so close, right? Their delta is 0.03. And so if I do 10 to the 0.03, that's real small. I said 0.03, I 100% meant 0.3. So our ratio here of A minus to HA, 10 to the 0.3 to 1, 10 to the 0.3 is only about 2 to 1. So it's like 33% this, 67% this at physiological pH. So now let's compare all of this that we've done with some other pKa's. So we have serine, which has a pK of 13. We have tyrosine, which has a pK of 10. And we have this molecule that has a pK of 7.4. So why do we get more acidic as we kind of go down with these three molecules? Does anyone want to throw out a guess or venture an explanation unmuted or just in the chat?
Sure.
Ding dong, welcome.
Is it because the others have, so basically like the number one is just a hydroxyl group. So its pK is close to like
what we would expect, right?
But yeah, but you got the other stuff going on there that's like not depicted that is withdrawing, right? But then the withdrawing groups get stronger and stronger with each subsequent molecule. Yeah, because that oxygen can donate its lone pair into the aryl ring.
Yeah, so you're right
And
that
then
there's
again-
donation, and it's donation via what mechanism? Like, how does it donate in? And maybe I should draw out these actual bonds here.
And it's like a conjugated pi system.
Yeah, and the golden word that I'm looking for is resonance. You are totally right. So I joke in my OChem 1 class that like 8 times out of 10, if we asked you why something's happening, the answer is resonance. So yeah, you're totally right. When we have a phenylalanine over here, we have a resonance structure where this can donate electrons in and move it around. So how does that affect our acidity? Well, let's think about our conjugate base. Our conjugate base, we have an O minus. We have an oxygen that has negative charge. It wants to spread out its electrons, and serine cannot spread it out. Like, it doesn't have anything it can do resonance with. But tyrosine can do resonance and push some of its electrons into this ring and spread it out across all of these atoms. So this negative charge on the conjugate base is more stable for tyrosine. And we see if we have more resonance, we have a more stable conjugate base. And using our acid words, remember we think about acids as either weak or strong. So if we are stable, we are a weak conjugate base. And the kind of golden rule of acidity, at least in my mind, is strong acids have weak conjugate bases. Boo, 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 boo. That was like the only thing I walked away from Gen Chem knowing. So if we have a weak or stable conjugate base here, we know that we have a stronger acid, and that's why we see a lower pKa, indicating a stronger acid here. Great. So now, what about from tyrosine to this molecule? So I heard induction. Like someone said that this is inductively withdrawing. Yes, but something else is going on. Anyone want to take a stab?
Is it also resonance?
Wow. 8 times out of 10, we haven't hit 10 yet. It is also resonance. So let's draw out this NO2. It's called a nitro group, and it's really helpful to see the structure. So it's a double bond to an O and a single bond to an O. The single bond O has a negative charge, and the nitrogen has a positive charge. So yes, it is totally going to be inductively withdrawing because we have all these electronegative atoms outside the ring. It's going to kind of pull electrons out. But also, we can push in, and push out of the ring on the other side and spread out our electrons of this negative charge even more than our tyrosine. So because we have more resonance, because we have more induction, we are stabilizing this conjugate base even more. And so we have a weaker conjugate base, which means that we have a stronger acid here. So that's why the pKa goes down even more. And you can imagine if I had put other electron withdrawing groups, like if I put another NO2 here, another NO2 here, it would go down even more, maybe to 3 or 2 or something. So cool. That's part 1. Part 2, we are dropping into another scenario. This thing has a pKa of 11. Figure out what we mean. So, do you think that it is the HA type? So this would be just HA, where we're talking about this nitrogen. Or do you think that this is the BH plus type, so it has a positive charge as an acid? The pKa of 11, do you think it's the HA type or the BH plus type? Put in the chat. Y'all aren't laughing anymore. Now it's blah, blah, blah. Maybe that's a cough or something. So, chatters, you were correct. It is the BH plus type. Can someone who put that tell me why you chose this rather than the HA type? Yeah.
First and foremost, in all honesty, I was doing the practice problems about 2 hours ago, and there's a whole paragraph mentioning if there's some nitrogen, it's most likely in BH form. But aside from that, also just kind of looking at kind of the trend of numbers, it seems a higher pKa kind of means less acidic, so probably more likely to be more basic.
Yes, but it's way more extreme than that, like a higher pKa. So 11 is like fairly acidic. It's more acidic than an alcohol, you know? So typically we have kind of 2 standard pKa's to know, and this is more from OChem 1. And if you go back to the acidity lecture from OChem 1, which is lecture 1 or 2 in the videos I sent out, I have a list on there where it's like, these are really helpful pKa's to memorize. Not to give you more things to memorize, but NH4 plus has a pKa of about 9. NH3, which would be removing one more hydrogen, has a pKa of 38. It is not very acidic at all. A neutral nitrogen is not very acidic. In fact, it's pretty darn basic, and that's what you're getting at there. But like this 11 number is nowhere close to that kind of basic 38 way up there in the stratosphere. So because of that, we know that this is going to be, we have NH2 plus, and we're using BH plus type. And then that means our conjugate base is going to be the neutral molecule that we were given at the beginning. So this is our B to the BH plus. Okay, cool. I'm not going to do the whole ratio and everything because that's like overkill. But let's compare this with a pK of 11 to ammonia, that's a pK of 9, or ammonium, I should say, and lysine, which has a pK of 10.5. So what's going on that's driving up the pKa as we go down? I will give you a hint. This is not one of the 8 and 10 times where the answer is resonance. So, what other effects do we know about with atoms that impact acidity?
Yo, Colton, can I take a guess?
Please, welcome.
Is it hyperconjugation?
Whoa, right out of the gate, dropping the H-bomb, hyperconjugation. That's 100% right. So we had this idea from OChem that if we had something like a carbocation, we always said that tertiary carbocations were more stable than secondary carbocations or primary carbocations because the neighboring sigma bonds, these sigma CHs, they would be like, oh no, your house burned down? You don't have any electrons? They're there. Maybe I'll lean my electrons a little bit closer to you. I'll donate just a little bit of electrons to you so that you feel a little bit better. This is the idea of hyperconjugation. So it's not like resonance. Resonance is like, we are your ride or dies. We will take on this charge with you. We will do resonance structures. We will rebuild the house. Hyperconjugation is a weaker effect. I like to think about it as the opposite of induction. If induction is pulling electron density away from something, hyperconjugation is pushing electron density a little bit towards something. And so the general idea here is alkyl groups are electron donating groups. EDG is a common abbreviation that we use, electron donating groups, via hyperconjugation. So this has no hyperconjugation pushing electrons towards it. This has one thing of hyperconjugation pushing electrons toward it, and this one has two. And so what happens when we're pushing electrons towards an acid, specifically an acid that has a positive charge on it? Well, we're stabilizing that positive charge, aren't we? We're giving electrons towards a positive charge that wants electrons. And if we are stabilizing these positive charges, we are stabilizing an acid. And a stable acid makes it a weaker acid. Unstable acids are the really strong acids. Acids that don't want to exist are the reactive ones. So that's why our pK is raising. It's becoming less acidic. Big slide, y'all. Big slide. Hyperconjugation and resonance being the kind of main reasons here. So, any questions on this before we go and do practice 2? Yeah.
I think I just got some wires crossed because I'm going through like the notes I'm making.
Yeah.
And when comparing like 1A to 1B, I was under the impression that resonance makes stuff more stable, but it also makes it more acidic. But you just said a more stable acid is less acidic.
Depends on what we're stabilizing. So here, we were talking about stabilizing the conjugate base. And so if we stabilize the conjugate base, which has a negative charge that needs to spread out, we're making a weaker conjugate base, and weaker conjugate bases have stronger acids.
Gotcha.
Whereas over here, we are stabilizing the acid itself, making it a weaker acid. Yeah. Cool. Okay. To be so honest with y'all, practice 2, I combined like 4 questions that were on the original section document, which I don't think has been posted. I don't know why it hasn't been posted. But I might have been ambitious with this. And I do really want to talk about protein folding. And protein folding, I think, will take me like 10 minutes. So I'm going to try to like plow ahead and be as clear as I can, but also I'm going to be like moving and grooving, and we're going to have a video that's recorded to kind of like watch back things. So yes, feel free to drop questions in the chat, but I'm going to kind of put it in a different gear. So practice 2 says we're giving you a small peptide chain, and we want you to draw this peptide chain at pH 1, 5, 10, and 13. So we're going to draw the peptide chain 4 times. If you're an iPad user, I mean for you to do this with copy and paste. If you are a paper user, we're going to draw it once, and then you're going to look at the section notes or the section video, and it's going to be like, oh, it has been copied and pasted, and you'll kind of see the idea from there. So please do not try to draw the whole thing 4 times in the like 8 minutes that we're going to do this. At each pH, we are going to determine the net charge of the peptide. So we are going to add together all of the charges present. So I have given it to you as 1-letter codes. Let's do some decoding here. Let's write the 3-letter codes, and then let's write out the structures. And then we will piece them together and do a polypeptide chain. So well, I remember that's glue, Glue. So that's glue. C is cysteine, the only one that starts with C. H is histidine, the only one that starts with H. R is everyone's favorite, arginine. Okay. Then I know glue is 2 carbons, and then I have a carbonyl. Cysteine is 1 carbon and an SH. Histidine, that's the one that's a pain in the butt to draw. So we have 1 carbon, and then we start to split off for our 5-membered ring. So we do a double bond, 1 bond to a nitrogen. We finish off our ring with another nitrogen on the other side. Then we make one of them NH, and then we make one of them a nitrogen with a double bond. Doesn't matter which. Arginine, it is 1, 2, 3 carbons, followed by a guanidine. So we have NH, NH2, NH. Cool. So we have this, and then what are these N and C over here? Well, those are our N terminus and C terminus. So we know we're also going to have like an NH2 and then like a carboxyl. And maybe I'll go ahead and draw them in the charged form here. So now let's draw our first like actual peptide structure here at pH 1. And at pH 1, we are so acidic that we are lower than the pKa of everything. So everything is in its charged form. So let me kind of talk you through my advice for drawing a peptide chain. So you start off with your N terminus. So we know we're positively charged here. And then you do zigzags. The thing next to the nitrogen is what's going to have your R group, but let's just do the backbone for now. So we have our alpha carbon that has the R group. We will have a carbonyl and then an NH. And we're going to keep going N, alpha carbon, carbonyl. So N, alpha carbon, carbonyl. Okay. N, alpha carbon, carbonyl. And see how they kind of like flip-flop each time? Like this time the amide is like right side up, then it's upside down. Okay, well we need 4 amino acid residues, so we're going to keep going with this. So N, alpha carbon, carbonyl, and then N, alpha carbon, carbonyl. And this is going to be our C terminus over here. So did I add too many carbons? 1, 2, 3, 4. I added 1 too many. Let me erase it. We only want 4 R groups on here. So we'll just erase the backbone. Cool. So now from here, we are going to put in the side chains. And the key here is if we have a valley for our R group, we're on a dash. And if we have a peak, we are on a reg. So we start off with glue. So we do down, 1, 2, carbonyl, carboxylic acid here. Okay, then we have cysteine. That's the wedge, and it's 1 carbon and an SH. Then we have his, which we're going to do down 1 carbon. We make our double bond and a bond to nitrogen. We finish off our ring and make one of them NH and one of them in double bond. And last one, arginine. So it's on a peak, so we do a wedge. 1, 2, 3. And then we do our guanidine. Ooh, ooh. But wait, we said everything needs to be in its most charged state. Well, this is neutral histidine. Where do we put the acidic hydrogen on our histidine? Because we're definitely lower than the pK of 6.4. It is going to go on the nitrogen that doesn't have a hydrogen. And my stupid way of remembering it is because that one's lonely. The other one already has a hydrogen. The actual chemistry is like, if you protonate this one, you lose resonance. But that's a longer explanation. And then for our arginine, we know that we are definitely going to be protonated. And we protonate up here at the very top. So at the double bond to nitrogen. So I made a handy dandy little table here to track our net charges. So at our N-terminus, we had a positive charge. Our glue, we were neutral. Our cysteine, we were neutral. Our histidine, we were positive. And our arginine, we were positive. And our C-terminus, we were neutral. So what's our net charge at pH 1? Well, we have 3 positive charge, so it's 3 plus. Cool. Then I am going to copy and paste here. And I'm going to make it a little bit smaller, actually. So now I have raised the pH, and I need to see which pKa's did I cross when I raised the pH. Well, let me draw in all my pKa's here just as a reminder. So our N-terminus we said was about 9, our C-terminus we said was about 2. Glutamate and aspartate have pKa's around 4. Cysteine's about 8. Histidine 6.4. Arginine is like 12 or 12.5. Something like that. Let me double check. 12.5. Cool. So when we went from 1 to 5, which of these numbers did we cross? Well, we crossed 2 and 4. So we know that 2 and 4 over here, they are going to become deprotonated. So they're going to go from neutral to negative charges. And everything else is going to be the same. So let's just trace those differences here. Neutral to negative, neutral to negative. So at our C term, we are going to deprotonate, make it a negative charge. Boop. And then at our glue, we are going to deprotonate, make it a negative charge. So those were the kind of changes we made to our structure when we copied and pasted. Now we can add up what's the net charge. Well, we have 1, 2, 3 plus and 2 minus. So our net charge is 1 plus. I'm going to do the same process, again, just kind of speeding through this. So now, and actually I'm going to copy and paste this one because it already has 2 deprotonations. But now we are moving from pH 5 to pH 10. And when we do that, we have to see which pKa's did we pass. So I'm going to cross off the ones we've already hit. We've hit 2 and 4. And as we go from 5 to 10, we now hit 8 and we hit 6.4. So we are going to deprotonate our cysteine. It went from neutral to now if we deprotonate it, it's going to be negative. And our histidine, if it was positive and we deprotonate it, now it's going to be neutral. And then everything else stays the same. Ooh, I'm so sorry, I forgot the N-terminus as well that we're going to deprotonate. So that's going to go from positive to neutral here. So the trend here that you'll see is if something is positive and we are deprotonating it, it becomes neutral. If it is neutral and we deprotonate it, it becomes negative. Okay, so overall our net charge, we have 1, 2, 3 minus and 1 plus. So we are at 2 minus. We need to now remove the hydrogens on our nitrogen over here. So we need it to be just NH2, because that's one of the ones that we deprotonated when we went to 5 to 10. We're going to deprotonate the sulfur, give it a negative charge over here. And then the other one that we crossed was histidine. So we're going to remove that second hydrogen and make it neutral over here. And again, we see that we have 2 negatives, 3 negatives, 1 positive. Last one, at pH 13, we are basically the most negative that we are going to be. The only thing that we have not deprotonated is our arginine over here. So our arginine, we are going to delete a hydrogen and its positive charge. And we are going to have this go from positive to neutral. So we have negative, neutral, negative, negative, neutral. And I've been highlighting these changes here. So only one change this time. Now we have 3 minuses. We're at a net 3 minus charge. So this is kind of the complicated way that you can see that all of this comes together with like amino acids, side chain pKa's, pH and pKa, and then charge. You can do things like, let's say you want to run this through a column with charged beads and like separate out this peptide from another peptide based on its net charge. Like there are a bunch of more kind of biochemistry things that you can do with this information. The last question I have on this scenario is, let's say we did a mutation in this amino acid chain. Which mutation here would be the least versus the most dramatic? So E is the starting for all of them, and that's our glutamate over here. And then Q is cutamine, right? So she has 1 carbon, and then she has an amide. D is aspartic acid, which is 1 carbon, and then a carboxylic acid. And then W is our tryptophan. So, can you vote in the chat, which do you think is going to be the least dramatic transformation? Number 1, number 2, or number 3? If we subbed out E for something else, which is going to be the least dramatic transformation? I'm seeing some answers in the chat. 2. That is exactly right. This is going to be the least dramatic because look at how similar it is to the amino acid that was originally meant to be there. All we did was delete 1 carbon, but we are still charged. And we are the same functional group. Now, what do you think is going to be the most dramatic change if we went from E to another one of these amino acids? Option 1 going to cutamine, option 2 going to, or 2 we said was least, or 3 going to tryptophan. Which seems like it's going to be the most disruptive and like really interfere with function? Ding dong. Most disruptive over here is going to be subbing out glutamate with tryptophan. 1, this is a whole heckin' lot bigger. 2, it's non-polar. We went from a charged amino acid to a non-polar large amino acid. And so if this was in a larger peptide sequence, these have functions, then we are going to definitely have a big change here by losing that. So with that, I'm going to pause here. So we are at the time for section. You saw in my email, hopefully, that I normally do 90-minute sections. So this is the time now where you can go. I will say, because this is a video that everyone can watch, I am going to spend 8 minutes and talk through protein folding. You are welcome to stay for that. You're welcome to head out, take a break, and leave for the evening. But either way, I will be back at 7:45 to do office hours. And I'll be around for an hour answering questions, come ask about the problem set or practice problems or whatever. But thank you for coming to section 1 if you were headed out. I really appreciate like such strong attendance for this. And hopefully it was helpful talking through some of these PHPKA, amide bonds, and amino acid things. So thank you. And I'll give like a minute here if people want to head out, or if you want to stay, you're welcome to stay. And I will be doing about 8 more minutes on this. Any questions so far too, if I'm taking a little pause for a second?
Hey Colin, sorry, I look at a question. It's related to the PKA value, something on the practice problems. So would you rather me wait till
I think
office hours?
probably office hours would be a better bet for that. Thank you though.
Gotcha. Thank you.
Cool. Well, if you're sticking around, I will hopefully try not to waste your time, but I want to give a recap of protein folding, why it happens, why do we care? So, to understand why protein folds, or why proteins fold, we are going to look at the common ways that molecules interact with each other. And in Gen Chem, we call these IMFs, intermolecular forces. You've seen all these before: ionic bonds, ion dipole, H bonds, dipole-dipole, and van der Waals. But one thing I'd like to add here to this discussion is like the relative magnitude order of difference of these. So on average, an ionic bond is going to be -20 to -40 kilojoules per mole. Whereas ion dipole, you can see immediately a big drop. It's going to be -5 to -15 kilojoules per mole. Hydrogen bonds can be quite weak or quite strong, so it can go anywhere from -2 to -20. So some hydrogen bonds can even be stronger than ion dipoles. Dipole-dipole, far weaker, -1 to -10 kilojoules per mole. And then van der Waals are weakest interactions, -0.5 to -5. My joke about van der Waals interactions is, like adults who do not like children, and the meme of like, why are they sticky? Why are these molecules sticky? Why do they stick to each other? They just do, is the short answer. The longer answer has to do with like instantaneous dipoles and is way more boring. So talk through these in lectures. Some of these IMFs appear in the 4 types of side chain interactions that we commonly see in peptides. So our 4 types of common side chain interactions that can happen are: we can have hydrogen bonds, we can have hydrophobic interactions, which are van der Waals interactions. We can have a disulfide bridge, which is actually a covalent bond. So it's not an intermolecular force because it has joined the molecules permanently. And then we can have ionic bonds, which are sometimes called salt bridges. So these are our kind of main interactions that the protein can make with itself when it folds. But we're trying to figure out why folding happens. And that's a question of thermodynamics. So we're going to go back to Gibbs free energy, very Gen Chem, very of the moment. I thought about getting a beanie that has this printed on it, but then I was be too ashamed to like wear it around. But like, love Gibbs free energy, so cool. So our delta G here is Gibbs free energy, which is our proxy for spontaneity. And so if delta G is minus, we are spontaneous. And for all delta G, delta H, delta S stuff on this page, if it is good, I have put a smiley face, and if it is bad, I put a frowny face, because I don't want the plus and minus to be like stopping processing speed here of like thinking about it. Delta H is enthalpy, and enthalpy is the potential energy that's stored in chemical bonds or intermolecular forces, which are types of bonds. So delta H being negative is our happy face, our favorable bonding interactions. Whereas if our delta H was positive, we would have unfavorable interactions, or we would have had to like spend energy with our bonds, making and forming. Then delta S is entropy. Don't get me started on entropy. I love entropy. It's one of my favorite concepts. Second law of thermodynamics is the entropy of the universe is increasing. And like anytime I like drop something, I'm like, wow, entropy really won today. Entropy is like we are complicated. We try to make complicated things, and so if doing complicated things fail, it's because the entropic cost was too high. Creating that order has a cost, and that is entropy. So entropy, broadly speaking, we term as disorder. And so because the universe wants entropy to increase, a positive delta S, which is our happy face, is something that increases disorder. So favorable entropy is increasing disorder, and unfavorable entropy is decreasing disorder. In other words, creating order, creating complexity, limiting freedom. So folding, a folded protein is super ordered. So let's look at protein folding in a vacuum. An unfolded protein, she's a noodle. She can wiggle. She has so much freedom. She said, wow, I am entropy. I'm Wiggle City. Whereas a folded protein is like you're in a yoga pose. You are in a very specific stance, and there are only one or two, oftentimes, acceptable states for a protein to be in. So to go from I am Wiggle Noodle to I am locked into a yoga pose, there is a high cost of entropy. So we have a big negative or frowny face, delta S. There's a high entropic cost for the order that goes into a folded protein. Whereas unfolded, we had a lot of entropy. We were great. Now, when we do fold, we do get some delta H that is helpful, some helpful enthalpy formed from our side chain interactions. But it's not enough to pay this cost. So something else must be going on. So protein in a vacuum, does it fold? No. We still have too high of an entropic cost. So let's talk about water, because proteins are not in a vacuum, they're in water. And really quick background, ice creates this really, really intricate crystal lattice structure where all of these hydrogen bonds kind of lock the water into a really rigid place. And it has a high entropic cost to be a solid, to be this ordered. And generally speaking, solids have a lot less entropy than liquids, which have a lot less entropy than gases. Another place that we see this idea of ordered water is in surface tension. So like adding drops of water to a penny. The surface of that water is going to be highly ordered like ice in order to maintain that tension. And what we see is the water at the surface is ordered, so there's a negative delta S, there's an entropic cost. But the water that's beneath it is called bulk water. It has way more freedom. It can move around. It has really favorable entropy. So, with this idea in mind of ordered water and bulk water, let's think about how water interacts with a peptide chain. So, if we have polar or charged amino acids, we're going to get a lot of hydrogen bonding. We're going to get some positive, or not positives, I should say, some favorable enthalpy from this, because you're going to have these favorable interactions of water interacting with the polar groups, hydrogen bonds, all this. But non-polar groups, water does something different. Like the surface tension, like the ice, it is going to form a cage around these non-polar residues. And the bigger the non-polar residue, the bigger cage that we have. And so whenever we have non-polar residues exposed to water, we have a really high entropic cost because it's ordering all this water compared to bulk water. These cages, here are some images of cages around specific molecules. These cages are often called clathrates, which you don't need to know that term. But look at how ordered the water is around this non-polar kind of benzene ring here. And if we use a space filling model, she's crowded. She is being swarmed by fans, and the fans are water. And you can see this is a cutaway here. But again, ordering water, creating these large clathrates, is going to have a higher and higher entropic cost. So with this in mind about water, how it interacts with peptides, let's now view protein folding in water, first through an enthalpy lens, and then through an entropy lens. So through the enthalpy lens, unfolded, water interacts with the protein. We have the favorable interactions. When folded, the protein has its side chain interactions, which is favorable, and then the water can replace its with hydrogen bonding among itself. And so you have favorable interactions on both sides, and they kind of just cancel out. Like, this is a little bit more favorable for delta H, but they're roughly the same. So if you are going to have favorable delta H on either side and they're roughly the same, is this going to be the thing that drives protein folding? Probably not. It's not going to be these IMFs. Instead, if we view it through the entropy lens, over here, remember, we have a lot of disorder on our protein, but our protein in water is going to have those clathrate cages, which is a pretty big entropic cost. We are ordering a lot of water for all the nonpolar residues. And I've only drawn some here, but imagine we have quite a few on our long peptide chain. However, when we fold, over here, again, we have an entropic cost on our protein of folding, like a negative delta S here, entropic cost of our protein folding and only having one orientation, whereas before it was a noodle. But water is so free. We have bulk water. Bulk, like all of the water that here was trapped in making these cages is now free. And that is a huge positive delta S. We are getting a lot more randomness by freeing up a lot of these water molecules to go and do whatever they want. And so the entropy of water is a really big payoff energetically. And that is what drives protein folding. The idea that by hiding nonpolar residues inside of a protein, you free up water to have a lot more entropy. And this is what we refer to as the hydrophobic effect. So we can see it here. Maybe first I'll read the summary. The hydrophobic effect is the process whereby burying hydrophobic residues releases ordered water, producing an energy gain that exceeds the entropic cost of folding. This is going to be the driving force of protein folding and why proteins fold. We had this diagram from class that said, this is the entropy cost of protein folding. So this is the delta S of the protein because it's becoming less random. This is the delta H that we get from our IMFs when we fold. But even if we ignored this, the result would still be the same. The hydrophobic effect is by far the largest effect here. This is the positive delta S that we gain by releasing that water to be bulk water. So with that in mind, very, very quickly, one of the questions here is, why, though hydrogen bonding is crucial for adopting secondary structure, is it not the dominant feature in the energetics of protein folding? Like, the answer is essentially the hydrophobic effect. This does not consider so far what's happening with the water. The water is really ordered in the unfolded state, and it becomes really disordered in the folded state. And then B here is, protein folding occurs in an aqueous environment. Given a short explanation why protein folding may not occur in a solvent like hexane. Well, there's no water, so there's no hydrophobic effect. Like, there's no reason for us to want to bury our hydrogen. So, no hydrophobic effect. But I went longer than anticipated. This is my first time teaching a lesson. So I'm going to end the video here and end section 2 for those who stayed. So thank you for coming or watching the section video. Welcome. It's so lovely to have you. And I'm going to stop recording.